call these ones level 2 permutations because they're just a little bit more difficult than the level 1 permutations. Okay, the whole idea with permutations is that you really have to pay attention to what's going on in the problem. What are they asking you to find? Does the order matter? Are you losing the number of options as you go down, or is it always staying the same? So you really just have to pay attention to the details. So let's take a look at these examples. So 3 couples go out to see a movie for Valentine's Day. They all sit next to each other in a row. How many different seating arrangements are possible if anyone can sit anywhere? Okay, so if anybody can sit anywhere, there's a total of 6 people, right? 3 couples, so 6 people. And if anyone can sit anywhere, that means that I have 6 slots because I have to make 6 choices, right? I have to choose who goes in seat number 1, who goes in seat number 2, who goes in seat 3, seat 4, seat 5, and seat 6. Okay? If anyone can sit anywhere, then I have 6 options for who goes in the first one, and then 5 options, then 4, then 3, then 2, then 1. It goes down every time because once you sit in a seat, you are no longer eligible to sit in the next seat, right? You can't sit in more than one seat at a time. Okay, so then we multiply all of that out, and that works out to 720. So there's 720 ways that these 3 couples can go see the movie. All right, but for part B, now we're going to say, well, it's Valentine's Day, so probably these people want to sit together. So there's a couple of different ways that you can approach doing this problem. Okay, so here's the way that I approach it. I look at it and I think, okay, well, that means that I have 6 seats, right? So seat number 1, seat number 2, so just like before, blah, blah, seat number 6, right? So now when I go to sit the first person down, I have 6 choices for who's going to sit there. Okay, but now what I know is that if this person is sitting there, this person has to be their date, right? So now I don't have 5 choices for who's going to sit here. It's got to be whoever this person was, it's got to be their date. So there's only one person who can sit in that seat, the date. Okay, once those 2 people are sitting down, now there are 4 people left who need seats. Okay, well, once that person sits down, then whoever sits here has to be their date, right? So I've only got one choice for who that's going to be. Okay, then I've got 4 people seated, so that leaves me with 2 people left, right? And then this person has to be their date. So if we're going to specify that it has to be the date, right, then it significantly changes things. So now I'm just multiplying 6 times 1 times 5 times, or 6 times 1 times 4 times 1 times 2 times 1. So 6 times 4 times 2, so that's 6 times 8, or 24 times 2, so 48. So there are 48 different ways that they could sit where they're just sitting with their date. Okay, so that is kind of what we're looking at with this one. So that is how I would approach this problem. Now, that's not the only way that you could approach this problem. Okay, it is a way that you could approach this problem, but it's not the only way. So you could also consider this as having 3 couples, right? And then from there, having to look at saying, okay, well, here's all the different ways that I can seat my 3 couples. And then once I have those, I have to figure out, well, how many different ways can I then rearrange those couples? Okay, so option number 2 to approach this one, which not how I would personally approach it, but I would look at it this way, where instead of having each slot representing a seat, I would choose a couple. So I would have couple number 1, couple number 2, and couple number 3. Okay, so I've got 3 choices because there's 3 couples, and then 2 choices, and then 1 choice, right? So that would work out to 6. All right, but from there, then you have to take into consideration that there's 2 different ways this couple could sit, right? Right, you could either have like person A and then person B, or it could be person B and then person A, right? And same thing here, you could have person C and then person D, or person D and then person C, right? So same thing here, right? They could go in either order. So I could approach it this way, and then I would have to multiply it by 2 for the 2 different ways that you could rearrange this couple, and another 2 for the 2 different ways you could rearrange this couple, and then another 2 for the 2 different ways you could rearrange that couple. And you would still get 48. Okay, so this would get you to the 6, And then this would be the number of ways to seat couple one, right? And this would be the same thing for couple number 2. And this would be the same thing for couple number 3. Personally, I find this way a little bit more difficult. I prefer to think of it this way, but you could go either direction with that. All right, next one's decks of cards. So first of all, you need to understand the anatomy of a deck of cards. Okay, so if you are not familiar with how a deck of cards is laid out, then you're gonna need to spend some time looking that up and making sure you know how they work. Okay, so there's 4 different suits, a total of 13 cards per suit, so 52 total, right? You got ace, and then a 2 through 10, and then jack, queen, king. Okay, so in this case, we're pulling 5 cards out of a deck. How many different permutations are possible if the first card has to be an ace? So we are choosing 5 cards. So I have 5 slots. This is card number 1, right? This is card number 2, and so on, right? But this first card, I know, needs to be an ace. So when I think about this, how many aces are in a deck of cards? 4. So there are 4 choices for my first card. Once I take that ace out of the deck, there's 52 cards total, but I just put one of them down. So that leaves me with 51 cards left for my next one. And then once I put that one down, 50 left, and then 49 left, and then 48 left. Okay, so that is what I'm going to multiply together to figure out how many different ways this is possible. So really big number, 244,90200. So 24 million. Okay. Question number 2. What if the first 2 cards need to be face cards? So face cards are jacks, queens, and kings. Okay. So we're still pulling 5 cards because this is all the same problem. We're pulling 5. Okay. The first 2 cards have to be a face card. So this is a face and this one's a face. Okay. So jack, queen, and king. But there's 4 different ones of each of those, right? So there's 12 face cards total. So I would have 12 options here. Once I put a face card down, there's 11 options here. And now I've put down 2 cards. These guys could be face cards or they could not be face cards. The problem doesn't specify. So it could be they're all face cards. These could not be face cards. It could be a mix. We don't really know. So once those 2 cards are down, I have 50 options left. Okay, and then 49, and then 48. And then I will multiply all that together. 12 times 11 times 50 times 49 times 48 works out to, again, a really big number. 155,232,000. So that works out to 15 million. Okay, and now this next one. So the difference between B and C. So part B says that the first 2 are face cards. Part C says only the first 2 are face cards. That word only is really important. Okay, that makes a huge difference. You got to watch out for any time there's that word only, just like with Venn diagrams, right? Because here, these guys could have been face cards or not. Now what we're saying is that we're going to pull these 5 cards, and these 2 have to be face cards, but these 3 have to be not face cards. Hey, Watson. Sorry, the mailman's going by. Okay, so the first 2 have to be face cards. So just like before, we got 12 face cards, and then we have 11 options left once we put that one down. But now this one can't be a face card. So I don't have 50 options left anymore because some of those 50 cards are face cards. If there's 52 in the deck and 12 of them are face cards, that leaves me with 40 that are not face cards, right? You got the ace through 10 for 4 different suits. So there are 40 cards left that are not face cards. And then 39 and then 38. Okay? So it's a little bit different if it's only the first 2 versus the first 2 are, but maybe so are the other ones. Okay? So throw that in my calculator, 12 times 11 times 40 times 39 times 38. And it's a smaller number. Right? This one's only 9 million. right? So you think about all these different arrangements. This is why so many different gambling games involve cards, because there's so many different possible outcomes. All right, next one. How many different ways can the letters of the word mouse be permutated? Space is in the wrong spot there. Right. Okay. So how many different ways can we permutate the letters of this word? Okay. So this is going to be a common type of problem. So the first thing I want to look at is just how many letters do I have, right? So 1, 2, 3, 4, 5. So we got 5 letters, right? So I have 5 spots. Okay. And I've got 5 options for my first letter. So this is the first letter. I've got 5 options for that one. Once I put one down, 4 options, 3 options, 2 options, 1 option. So that's just 5 factorial. And again, you could either type all that out in your calculator, or you can just do 5 and then go to your math menu, go over to probability, and then option 4 is your factorial button. So you could do that either way. So that works out to 120. All right, and then this last one, so a similar problem, but this time we're looking at the word heroic. Okay, so how many different ways can we rearrange heroic? Well, I've got 1, 2, 3, 4, 5, 6 letters, right? So I know I'm going to have 6 slots, and 6, 5, 4, 3, 2, 1, which works out to 720. And there we go. All right, now one thing that I want to point out in terms of these word problems, notice that there are no repeated letters in either of these words. Okay, so mouse and heroic, there's no repeated letters. That will make a big difference. Okay, so you should always check for that. Later, we will talk about how you deal with ones where there are repeated letters. Okay, but for right now, just make sure that you're making note of that. Okay, the hardest thing about this unit is telling a permutation from a combination. So far, all we've done is permutations. So you're probably not paying a ton of attention to what the structure of the problems is in terms of deciding whether the numbers go down or stay the same. Okay, but that is going to be a really important thing for you to be focusing on. Okay, so you really need to make sure that you're trying to really pay attention. Don't just assume that you can just start dropping the numbers. Okay, really pay attention to the structure and figuring out why you're doing things instead of just what you're doing.